We introduced Fourier series in the last video. I'd like to do a couple more examples of finding Fourier series in this video. Here's our first example. Let's find the Fourier series for the function f of x, which will be the unit step function times L minus x on the interval from negative L to L. So if you draw a picture of this function, it would look like this. On the interval from negative L to L, the function is 0 up until you get to 0. Then, for positive values of x, I have the function L minus x, which is a diagonal line going like this. So this is my function, f of x. The Fourier series, here's my answer. The Fourier series is equal to a constant a0 over 2 plus the sum going from 1 to infinity, some constants an times cosine n pi over Lx plus some other constants bn times the sine functions sine n pi over Lx. Here, the coefficients an are given by 1 over L times the integral from negative L to L of my function times cosine n pi over Lx. Now, this is the unit step function, which is giving me 0 until I get to times 0. So that means this integral is really 1 over L, the integral from 0 to L minus x times cosine n pi over Lx dx. And I integrated this before the video began, and I got the following answer. So this is equal to L over 2 if n is equal to 0, and I've got 1 minus negative 1 to the n over n squared pi squared times L if n is bigger than or equal to 1. Notice when n is equal to 0, I have cosine 0x, which is just 1, and I therefore don't have this cosine term, and I'm just integrating from negative L to L the function f of x and dividing by L. That is almost the average value of the function f. It would be the average value if I divided by 2. That's sometimes also why I have this division by 2 in the first term. Nevertheless, the bn term is a similar calculation. It's 1 over L, the integral from negative L to L, f of x, but this time times sine n pi over Lx dx. You can express it this way, then integrate. I integrated before the video began, and I got L over n pi. And that holds for any n 1 or larger. So, the Fourier series, I can write down. I have all the coefficients. Therefore, the Fourier series is L over 4, I'm using a0 over 2 there, plus the infinite sum, n going from 1 to infinity, 1 minus negative 1 to the nl over n squared pi squared. That's my coefficient of cosine x. So that's my coefficient times cosine n pi over Lx. Then I have the coefficients in front of sine, L over n pi sine n pi over Lx. So this is my Fourier series. I was able to express my function as a combination of sines and cosines. Let's finish this video with one very simple example. What if I asked you to find the Fourier series for how about the function f of x is 17 minus 2 cosine 9 pi over L x plus 14 sine 10 pi over L x. Again, on the interval from negative L to L. Well, this is an almost trivial problem because I already have a Fourier series. This is the answer. I'm not going to express it as a big infinite sum because this is the Fourier series. I've already expressed my function as a combination of a constant, so that's the first term, plus some sine and cosine terms. So this is it. This is already a Fourier series. I'm already done. It is a Fourier series already. Now, if you'd like, you can go through and do all the integral calculations, and you'll find that most of these coefficients are 0 in this infinite sum, and you only get non-zero coefficients when you have n is equal to 9 and n equals 10. All right, excellent.